Good morning, grade nines. I hope you're enjoying what's a beautiful day today. I hope you are able to get outside. I know that we're practicing social distancing, and now they're saying to wear masks and everything else, and this is a really strange time that we live in. But anyway, I hope you and your families are doing well, and I really wish that we could be together for me to show you these demonstrations and stuff like that, because it's a really cool thing. Okay, so anyway, and it's a favorite among my students every year. So anyway, how do musical wind instruments work and stuff like that? Well, that's what I'm here to explain to you today, and it's the last lesson in the sound unit. Well, we're going to do something on ultrasounds too, and scanning technology, but like for the official sort of sound unit, I think you'd be happy to know that this, because I know it's been some of the questions are a bit challenging. But and this one, I think you'll find interesting though, how musical instruments work. And I made a series of videos for you here, but I'm going to show you some of that. In my hand, I have a test tube. Okay, and you can sort of picture what a test tube looks like, right? It's a little tube of glass. It's closed at the bottom and open at the top, so you can put things in it. But I'm not here to do a chemistry experiment with a test tube. I just want to show you that any hollow tube, and you know this because you've done it before with like a bottle or something like that, where you open up the top. And if I blow over the top, it makes a musical tone. Okay, that's resonance in tubes. Okay, so before I get into the lesson here, and it's going to take me a while to go through this, but before I get through it, I want to remind you of something that we did before, and that's resonance in strings. So this would have been when we were actually together. And I'm just going to play this video for you here. You can look at these videos on your own. I posted them all in OneNote. I'm going to mute the audio. Okay. So yeah, if you remember how resonance works in strings, okay, you can watch this video and you can see the different harmonics and stuff like that. And so resonance in strings, right? So that's the first harmonic. And if you wait here a little bit longer, you'll see other harmonic modes. I'm just going to sort of skip to it. See, there's the second harmonic in the string. And so what I did was I created a short video to review resonance in strings. If you want to go on OneNote and just play this video and look at it, you can do that. It talks about nodes and antinodes. So there's a node and there's antinodes. And if you remember, an antinode is half of a wavelength. And a node is, you always get nodes that are separated by half of a wavelength, right? And the reason why this is important to remember is because we went through this in detail. I showed you that really cool demonstration with the strobe light and the strings, and we looked at resonance in strings. Okay, so I'm going to pause that video. Yeah, and just this is a little summary. Okay, so a little summary of resonance in strings. This is the first harmonic. Okay, so I don't know if you remember. Oh, that's terrible here. I'm going to move my keyboard so I can write better on my screen. Okay, so this is the first harmonic. And with the first harmonic, we see a couple of things. We see that half of a wavelength, like one crest or one trough, is one half of a wavelength. So the length is a half of a wavelength. That's what it says here. Okay? And this is the first harmonic. Okay, and the first harmonic mode has one antinode in it. Okay, this is for strings. Okay, for strings. So the first harmonic has one antinode. Now the second harmonic has two antinodes. So here, now we have two halves of a wavelength. Pardon me. Let me fix that. Okay, so the distance across is two halves of a wavelength. Well, two halves of a wavelength is just one wavelength. Okay, so that's the second harmonic. And the third harmonic has three antinodes and three halves of a wavelength, right? The fourth harmonic has four halves of a wavelength, and so on. Okay, and so that's how resonance in strings works. These fixed points are called nodes, and these things here are called antinodes. All right, so that's resonance in strings. Now, what about in hollow tubes? Well, I made a video for that too. There's a really cool website that you can go and play with it. I put a link to it in the video. But anyway, I'm going to show you this. I'm going to mute the audio. Yeah, so the audio is muted. Okay, so this is just a website you can go to and you can look at hollow tubes. And what I'm showing you here is that see these dots at the top are air molecules. So that's my test tube, that black tube at the top with the closed up at the bottom. When you blow over the top, it creates a standing wave in the air molecules in the tube. Okay, and that's how wind instruments work. And so what's happening here is we don't get the full antinode. Okay, sound waves are longitudinal waves, so they don't look like nodes and antinodes. We don't get the full antinode, we get about half of it. Okay, so the first harmonic of this tube only has half of an antinode that fits across it. So that's a quarter of the wavelength. Since one antinode makes a half, then half of a half is a quarter. So this is a quarter of a wavelength of the waves. Okay. Now, if you look here in the video, I show you the upper harmonics a little bit later. Okay, so here this was the second harmonic of the, or I shouldn't say second harmonic, it's the next harmonic of the tube. Okay. And then if you blow harder, you get this, and there's a stationary point where the air molecules aren't moving right here. That's where the node is. Okay, so here you have one antinode plus a half of an antinode. That makes 3/4, okay, of a wave. And here I went to the next harmonic, and you get 2 full antinodes plus another quarter. Okay, and if you watch this video, you can see I go through the whole thing and explain like what you're seeing here, okay? And then I switch, at some point, you can switch this and you can look at what happens if you have the tube that is open at both ends, okay? So a tube that's open at both ends is kind of cool how the harmonics work. It looks like this. This is the first harmonic of that tube. It's open at both ends, and in fact, most musical instruments would be open at both ends, okay? If you play the trumpet, when you put a mute on the end, you close the end, but usually you're blowing into an open end and the other end is open. And there's a reason for that, but I'll explain later. But if you play this video here, I posted it on OneNote. You can play the whole thing and I do a little commentary with it. And you can see how these harmonics work. This is the first harmonic. And then when we get to the second harmonic of an open tube, you get more antinodes that show up, okay? But the end behavior always stays the same, okay? So anyway, we can see that strings have resonant modes, but tubes also have resonant modes. Okay, so I think you're going to like this one. I'm going to pause this video here. And then this one here, this is one of the projects that my grade 9s did last year for the open house. And this time I'm going to turn on the sound. I don't know how well it's going to work in this video. I guess I have to play it. Yeah, so I'll play the video. What you're going to see here is a tube that we constructed that's closed at the end. So it's like a gigantic test tube. We drilled a bunch of holes along the top so that gas could escape from the top. And then it's gas from the Bunsen burners in the lab. And so what I did was we lit the gas as it came out. And you can see the standing waves, the nodes and antinodes, in the fire. Okay, so take a look. And I'm going to unmute it if I can. All right. So that's actually in the physics classroom at our school from last year. The grade 9s built that.
Wow, that's awesome.
And you can see very clearly the nodes and antinodes. Now there's other videos online if you really want to see other Rubens tubes and stuff. The one we made was pretty good, but that's it. Okay. So now what I did in OneNote was I added other pages for you to fill in. Okay. So let me do some of this for you, and I wish we were together because it's a lot easier for me to explain this when we're together, but you know, we'll do the best we can. All right, so let's just read this first paragraph. It says standing waves consist of nodes and antinodes. Positions along the medium which appear to be stationary are of course nodes. Okay, now the positions where you get maximum positive and negative displacement are known as antinodes. Okay, so you know that already, right? And each consecutive node is always separated by 1/2 of a wave. So this is what we learned in resonance in strings, so it hasn't really changed. Okay? All right. Now, if you read the next paragraph, okay, at the open end, the air is able to vibrate back and forth. Okay, this forms an antinode at the open end. Okay, so antinode, not node. Okay, at the closed end, you get a reflection at the closed end of the waves, and that creates destructive interference. And so you get a node at the closed end. So the rule for, like we call it, the edge behavior, when you have a test tube-like tube, where it's closed at one end, open at the other, is you get a node at the closed end all the time, and an antinode, okay, at the open end. Okay, so let's fill in these pictures, and I'm going to do some of these for you, and I'll explain why the harmonics are numbered with odd numbers. There's no even harmonics in a tube like this. Okay, now I'm not very good at drawing these things, but if you remember what I did in class, so what I do is I have to do it like this, okay? And then you draw the other half of the wave like this. Now that's the first harmonic, okay, in a closed tube. Okay, maybe I'll use that different color moving forward here. But that is a quarter of a wave. It's 1/4 of a wave, because a full antinode would be half of a wave, but we only have half of a half. Okay, so that's a quarter. Now, if you just do a little math here and you solve this for wavelength, just multiply both sides by 4 and you get 4L. Okay, now I'm going to switch to the rainbow color because it's pretty, right? All right, so now in the next harmonic, we're going to get a node right here in the center of that tube. And so what's going to happen is I'm going to have a wave like this, and then its opposite looks like that. See, notice at the open end, I always get the middle of an antinode here. And at the closed end, I always get a node. Okay, now here there are 2 nodes. So how many wavelengths do you see here? Well, from node to node is half of a wavelength. So this is 1/2 from here to here, plus, and I haven't drawn it very well, I'm sorry, plus another, this should be shorter than the other one, but this is another quarter here. So a half plus a quarter is 3/4. Okay? Now if I solve that, like so, if I cross multiply and I just do a little algebra and I solve for wavelength, I get 4. Here, let me do it like this. I get 4/3L. Okay? So remember, you're going to multiply both sides by 4 and divide both sides by 3. So that's what I get. All right. Now, in the next mode, I have 2. Okay, I'm going to draw this a little better. 2 nodes. Well, actually 3. Okay, because the fixed end is always a node. Now, so my one wave is going to look like that, and then it always ends. Here, let me fix that. So it's going to go like this, like that. That's better. Okay, I want that. And then I'll draw its opposite. Trying to stay inside the tube. There, I've drawn that a lot better. So if you look, I have a node here, a node here, and a node here. Okay, I'll just put little dots. Okay, those are my nodes. And in between those nodes are antinodes, right? So one antinode, from node to node is half of a wavelength. So it's a half plus a half plus a quarter. Okay, so a half and a half make a whole plus a quarter. That's 5/4. Like that, 5/4 of a wavelength. And then here, I'm going to write 4/5L. Okay, when you take the reciprocal of that fraction because you're solving for wavelength, right? All right, so I'm going to keep going. The next one I'm going to get, like, instead of these 3 antinodes, I'm going to have 4. So you're always adding, like, okay, so here 1, there's 1 there, 2 to there, 3 to there, 4 to there, okay? Just let me rearrange that slightly. 1, 2, 3, 4, like that. So now I'll draw the wave, and I'll just zoom in because I'm not good at drawing. like that, and then I'll draw its opposite. Okay, and it looks like this. So here we see one node, two nodes. Okay, you know what? This is getting hard to draw. Okay, so let me bring back that wave. So let me go back to this. Is this a smaller point? No, it's not. That's much smaller, is it? So what I'll do is I'll just change the size of my pen. All right, so here, there's a node here, there's a node there, a node here, a node here, and a node there. Okay, so I have half plus a half is a whole, plus another half and another half makes two wholes. So that's 8 quarters. Oh, you know what? I didn't do this right. Pardon me. I need to fix it. I don't want to restart the video, so I'm just going to fix it myself. All right, I have 1, 2, 3 dots here, so I'm going to have 4 dots in the next one. So 1, 2, 3, 4, like that. Okay, evenly spaced. And then I'll draw my wave. I skipped a harmonic, that's why I needed to fix it. There, that's one wave. And then the other half of the wave looks like this. Okay, and here we can see I have nodes here and a node here, so there's a total of 4 nodes there. And then I have 1 half, 2 halves, 3 halves, and a quarter. Okay, so we always end with that little quarter there. Okay, so 3 halves makes 6 quarters, so this would be 7. Go back to my rainbow. This would be 7 quarters of a wavelength, or 4/7L. Okay. Now, if I do the next one, okay, normally I would get you to draw these after you see the pattern, but whatever, I'll just do it. So here we're going to have 5 nodes in the next one, right? So we started with 1 node, then 2, then 3, then 4, and now the next one's going to have 5. So I'm just going to evenly space them. 1, 2, 3, 4, and 5. Okay, that's 5 nodes. And now I'll zoom in to draw this better. Okay, like that. And then I'll draw the opposite. Like that. And then let's label the nodes. There's 1, 2, 3, 4, and 5, like this. And then if you look at how many wavelengths I have, this is a half, 2 halves, 3 halves, 4 halves, and a quarter. 4 halves make 8 quarters, so that's 9 quarters. Okay, now 9 quarters of a wavelength, or 4/9L. Okay, all right. So if you look, I'm sorry, it's a little laggy today. So if you look at this, there's a pattern. Okay, and the pattern's pretty obvious. So if you look at the pattern in the numbers, I mean. So in the first mode, you have 1/4 of a wavelength that fits across it. In the second one, 3 quarters, then 5 quarters, then 7 quarters, and then 9 quarters. So you start with a quarter, and then you add halves all the time. Okay, so the next one would be 11 quarters, and so on. Now notice how the numerator is always an odd number, 1, 3, 5, 7, 9, and so on. That's why the harmonic number, okay, here, odd only, okay? Only odd harmonics are present. We don't have any even harmonics. It's because the numerator is always an odd number with a close-ended tube, okay? All right, so if you remember, I want to remind you of something of resonance in strings, okay? That I'm going to switch back to a black pen here. So it says, these questions here at the bottom, it says determine the frequency of the third harmonic. So it's the third harmonic for an air column whose first harmonic is 262 Hertz. Well, if you remember, the harmonic frequencies for strings, you probably forgot this, but it goes like this, that the frequency of the nth harmonic is just n times the frequency of the fundamental. Okay? So therefore, if the fundamental is 262, what's the third harmonic? Well, it's going to be 3 times 262. Now I'll let you work that out with a calculator. Okay? Now, what about this one? The first harmonic for an air column whose fifth harmonic, okay, so 5, what they're saying is 5 times the fundamental is 1700 hertz. So what would be the fundamental then? And I will let you figure that out. Okay? So I will let you do these other two questions. So please fill in these blanks. Remember that the harmonic numbers are always multiples of the first harmonic. So for example, if the first harmonic is 10 hertz, then the second one would be 20, and the third one 30, and so on. Okay? Now these closed tubes only have odd harmonics. Okay? So that's it. Now, how about this? Okay, so these are questions. It says determine the wavelength of the wave in this column. Okay, so how many waves do you see here? We know the whole thing, it says in the question, that the whole thing, the whole tube, so let's say it's like my test tube, is 35 centimeters long, right? Okay, now it says, what's the wavelength? Well, how many wavelengths do you see here? Well, it's going to be, you know, from here to here is a full wavelength, but here is a quarter. So this is 5 quarters. It's a half plus a half plus a quarter. So this is 1/2, this is 1/2, but this is 1/4, right? So what you're going to say is that 35 centimeters equals 5 quarters of a wavelength. And then your job is to solve this equation for wavelengths. So you're going to multiply that times 4 and divide by 5. Okay? Now what about in this one? Well, how many wavelengths do you see here? Well, the whole thing is 56 centimeters long, so it's half a meter long, pretty much the tube. But how many wavelengths is it? Well, this is a half, this is a half, this one's a half, but that one is a quarter. Okay? So you've got 3 halves. That's 2 quarters plus 2 quarters plus 2 quarters is 6 quarters plus a half. That's 7 quarters of a wavelength, right? So just go ahead and solve that for wavelength. Okay? It's just simple math after that, right? Okay? Now it says, letter C, the first harmonic for a 32 centimeter long air column, closed. Okay? The first harmonic, you have to draw them. Okay? So it says, determine the wavelength. In the second one, you're supposed to draw the picture that you see up there. Okay? Oh no, pardon me. No, you don't have to draw it. I'm sorry. I'm making a few mistakes in this video. I'm just reading the question now and understanding what they're trying to ask. They're not drawing it for you, but they're saying it's the first harmonic. So now we'll use the table. Okay? So in the table, the first harmonic is 1/4 of a wavelength, right? So now we go back to this. And so now without having to draw it, we're just going to say that 1/4 of a wavelength is equal to 32 centimeters. That's the length of the tube, right? So solve it for wavelength. I will let you do that, okay? Now it says the fifth harmonic wave pattern for a 1.2 meter long air column. So what they're saying is the fifth harmonic is 5 quarters of a wavelength. The fifth harmonic, the numerator is 5, equals the length of the tube. So that's equal to 1.2 meters. So just solve it for wavelength. See? Pretty straightforward, right? Okay, so now it says the test tubes have a gig. I'm going to do one of these for you, and I'm going to see if you can do the rest, okay? So I'm trying to do most of it. I'm trying not to make your work too hard. I'll do a couple of these, okay, just so you get the idea. And then we'll leave this video here for now, and then I'm going to leave you that for homework, okay? And then I'm going to post another much shorter video where I will show you how to do the other type of air tube, like the musical instrument one, where it's open in both ends. Okay, so, and that one's really fun because we'll talk about musical instruments there. All right, so the test tubes have a gig in the park, so they're playing test tubes. The lead instrument test tube is 17.2 centimeters air column. The speed of sound in the test tube is 340 meters per second. Find the frequency of the first harmonic. All right, so here is this kind of question. You go like this. We're going to use V equals F lambda. Okay, that's going to be one of our equations. And the other equation we're going to use is that the length of the tube, if it's the first harmonic, is 1/4 of a wavelength of the waves. So we're going to do this first and this second. Okay, so watch. Step 1. Okay, if L equals 1/4 of the wavelength, let's plug in the numbers. That's the length of the tube. Okay, so we're saying L is 17.2 centimeters long. We're going to convert that to meters because notice my speed is in meters per second, not centimeters per second, so I have to use the same units. So I divide by 100, okay? And then you end up getting that 0.172 equals 1/4 of a wavelength. Now, I'm going to solve that for wavelength just by multiplying both sides by 4. And so 0.172, now you guys should be pretty good at this kind of math. I get 0.6, the wavelength of the waves. So therefore, the wavelength of the waves equals 0.688 meters. Okay. Now, I'm going to step 2, go to my universal wave equation, but I'm going to solve it for frequency. So frequency is equal to speed divided by wavelength. Well, it says the speed is 340. So that's going to be 340 divided by 0.688. Okay. So I'm going to do that on my calculator, and I get 494.2 hertz. Okay, and that is the frequency of the first harmonic in that tube. So it's kind of cool how that works. It's kind of like my test tube here, right? Where you get a certain pitch depending on how long the tube is. The longer the tube, the lower the pitch. Okay. So anyway, there you go. That is a sort of typical resonance in tube questions. Now, if you look back at resonance in strings back in OneNote, you'll see that we did stuff like that already. Okay. Anyway, I'm going to let you try the other 2 questions there, but I just want to do one of these for number 10. Okay. It says the sound produced by blowing over the top of a partially filled pop bottle, which is probably where you've done this before. Okay. Carry a tune. Uses 4 bottles labeled A, B, C, and D with various amounts of water. So if you can see her picture there, that is a typical thing that people can do, okay? Anyway, so it says varying amounts of water, that's air. Express your understanding of closed-ended resonance by filling out the column below. Okay, so here's the deal. The length of the column, now that is not how much water is in it. People get easily confused. It's how much air. So this is how much air. You put water in to make it shorter, right? So if the length of the column, the shortest one is 0.06, so it's just 6 centimeters. That is this one up here, okay? It's 0.6 centimeters. Or sorry, it's 6 centimeters or 0.06 meters. So if it's the first harmonic, okay, then we know that 1/4 of the wavelength will equal 0.06 meters. So multiply both sides by 4. I'm just going to put a little line here. Therefore, the wavelength is going to be 4 times 6 is 24. So the answer is 0.24 meters. Okay. I'm sorry, I kind of ran out of space there. All right. Now, if the speed of sound is 345 and at room temperature it's around 345, then to find the frequency of the fundamental, I'm going to go frequency equals speed divided by wavelength. Here, you know what, let me zoom in to make that better writing because it's not looking so good right now. So V over wavelength like that. So that's equal to 345 is the speed divided by 0.24 is the wavelength. Okay. So 345 divided by 0.24 equals 1437.5 hertz. All right, so now that I've done one for you, see if you can figure out the rest of these, okay, and fill in all the blanks. So I did the first row for you. Now, okay, I'll tell you what, because it's the pandemic, I'll give you a break on the second row, because I feel like answering that for you, okay? So look, what if you're given the frequency and you need to figure out what length you need? And we would have done this experiment in class where we do a little test tube band. Like I said, it's really fun. But anyway, we do like a test tube choir in school, and I'll get you to fill out, I'll assign you a frequency, and you have to put the right amount of water in the test tube. But anyway, how much air does she need in this pop bottle to get this frequency of 708 hertz? Okay, well, let's find out. Okay, so she got 708 hertz, so we're going to work our way backwards. We're going to use the universal wave equation. Okay, so what we're going to do, this time solve for wavelength. Wavelength in the universal wave equation is going to equal V over F. Okay, so here you've got the frequency, 708 hertz. This is V over here, right? So I'm going to go 345 divided by 708. 345 divided by 708 is 0.487. So this is 0.487, okay, meters is the wavelength. Now that I have the wavelength, how do I find the length? Well, the length is 1/4 of the wavelength. So now I just take that number, 0.487, so it's the first harmonic all the time. I divide by 4, and I get 0.122. So about 12 centimeters. So that's how you do it. All right, guys, I'm going to stop there for now. This video is getting very long, so I hope that helps, and I hope you're having a good week, guys. And I'm going to upload another video tomorrow to finish off the air columns thing. I might make it 2 videos, we'll see, but don't worry, like all of this you can just upload to OneNote at the end of the week. I have a couple of questions to assign for you on this, and there's some textbook homework too, and then that'll finish it off. All right, guys, have a good day. We'll talk to you later.